All right, as of now, we will begin for the distance learners. Today, we're going to be discussing particle physics and reviewing quantum mechanics. So, if you remember last time, we began to discuss the elementary particles, which are the basic constituents of matter, and they form other substances. And we don't know their inner structure, whether they're composed of other particles. So, elementary particles can be thought of as small spheres, but we don't really know their shape because they're incredibly tiny. And they can be categorized as fermions and bosons, as you can see right here in this next slide. These are different types of elementary particles in different generations of matter. So if you remember last time we discussed the quarks, which there are 6 different types of quarks. And we also have the other type of particles called leptons as well, right? And these quarks and leptons, there's like 6 of these leptons, which include the neutrinos. And they also have the antimatter parallels, which are all these anti-quarks, along with like the positron and the anti-muon, as well as antineutrinos. And then finally, we have the force carriers, which include the gluons, photons, and other particles that they're exactly as they sound. Right? They carry different forces like electromagnetism, gravitation, the nuclear strong force that we were discussing last class, and more other forces.
So the other kind of, other than quarks, there's also leptons. And for these elementary particles, um, they there are 6 kinds of them. So you have electron, muon, tauon, and the neutrino of them. And you can see in the chart the mass, the unit of mass here is electron volts over speed of light squared. So that is according to the equation E equals mc squared. So m would equal to E over c squared. And they have a they're very light. And the charge is -1 and spin is half for all of them. For the first row, and for the second row, the neutrino version of them, they are lighter and they have no charge. So first, we know electrons. We're familiar with them. Electrons are a fundamental building block of matter, which is bind to nucleus via electromagnetism. And then the muons and tauons are heavier and unstable versions of electrons. So practically, so what do they do in like real life, right? Where do we find them? We find them in a lot of cosmic radiation. For example, for muons, uh, they make up a lot of cosmic radiation, and the discovery of them was from these astronomical observations, and they're usually emitted from very extreme events in the sky. And for tauons, they are discovered here at the Stanford Accelerator, and the muons are about 200 times heavier than the electron, and then tauons are 17 times heavier than muons, so more heavier than that. And so on the next slide, we are going to talk about the neutrinos of the 3 particles. So leptons, they do not take part in strong interaction. They only interact via the electromagnetic and weak forces. So unlike quarks, um, these you can think about electrons. They only interact with electromagnetic and weak forces. So uh, mm, this makes them less influenced with a lot of strong interaction in the universe. And what this results in is that we can, because they never changed much, so their motion or their trajectory over time do not change, and we can use them as mediums to observe the ancient universe, because this is basically the universe sending direct message to us, and there's no influence because of how little they interact. But that also means it's hard to discover them because of how small they interact. And furthermore, neutrinos, they interact even less than the normal electrons, muons, and tauons because they have no charge. So they don't have magnetic interactions either. So um, that means they are a great carrier of information, like we discussed. So in 2017, the Ice Cube Neutrino Observatory discovered a source of neutrinos from a monster black hole, a very extreme event, and documented on the NASA website. And the Ice Cube Observatory here is a very special device they use to discover neutrinos. Because, yeah, so you can see the inclusion of 6 neutrinos here, 3 neutrinos, and 3 of their antimatter counterparts.
All right, now we're going to discuss a key building block to our discussion of antimatter, and that's from the electromagnetism unit when we were discussing the proton collision. When you have like two hadrons, two protons specifically, colliding with one another, and you can see the E equals mc squared in this photograph, where you have those two particles and they're colliding with one another, and you have the new mass formed from the collision because of all the energy. So we have this new mass formed from the collision, and this is actually a very key idea in antimatter as we discuss this. So in the Big Bang, you have both matter and antimatter, right? Because there's large amounts of energy when the universe is being formed. And so both matter and antimatter, which is like an opposite, are theorized to be formed. And so similarly in our CERN, when we have a particle collision, you can have both matter and antimatter. It's for incredibly small amounts of time. You can have both matter and antimatter, right? And antimatter is incredibly reactive with matter, right? And so it's very hard to store the antimatter because of that. They're incredibly reactive because they're like opposites, right? And so antimatter has the same mass, like all these antiquarks have the same mass as their quarks, as the quarks, but they have opposite electric charges. And you can kind of see the values here in the tables. And so they're also incredibly reactive. Like if you have like the size of like a gram of antimatter, like the size of a raisin, then you could blow up like, it's almost like a nuclear bomb kind of reaction, right? Where you blow up like the radius of New York City, for example. Like that's how reactive it is, just to give you an idea of scale, for example. So yeah, incredibly reactive.
And finally, we have the force carrier particles, which are the particles that mediate the 4 fundamental forces. And there are 4 force carriers corresponding to each fundamental force. So the photon carries the electromagnetic force. It's massless and has a spin of 1. The gluon carries the strong force, and it also is massless and has a spin of 1. The W and Z bosons both carry the weak force, and they're the only force carrier particles that are massive. They have a mass greater than 80 GeV, and they have a spin of 1. And finally, the graviton, which is only a hypothetical particle, hypothetically carries the gravitational force. And this particle is also massless and has a spin of 2. In terms of strength, of how much stronger each of the fundamental forces are, the strong force is the strongest, and then electromagnetism, and then the weak force, and then gravity. To put this into terms of numbers, if we just say the strong force has a strength of 1, the electromagnetic force has a strength of 10 to the negative 3, the weak force has a strength of 10 to the negative 6, and gravity has a strength of 10 to the negative 9. And in that link there, it just kind of gives a nice overview of each of the force carrying particles and the different forces. So now we're going to do a review of quantum mechanics, which we covered near the beginning of the year, but we're just going to review it now. So quantum mechanics is the study of subatomic particles and how they interact with each other. Quantum mechanics is different from classical mechanics in three main ways. Classical mechanics has continuous energies, whereas quantum mechanics has discrete energies. So it can only be specific values, not just any decimal number. Quantum mechanics has wave-particle duality, meaning that particles exhibit the behavior of both particles and waves. And finally, quantum mechanics has uncertainty, which we will elaborate more on now. So the Heisenberg uncertainty principle. Heisenberg, a physicist from the 1920s-ish, wanted to base his ideas on experimental data. And so to do this, to represent his data, he used matrices where each matrix element is a different experimental result. And through his use of matrices, he realized that they do not commute multiplicatively. So like A times B is not the same as B times A. So order matters. And so he took this fact that matrices do not compute and applied it to the physics. And in doing this, he found that the order in which you measure quantities matters. For example, if you try to measure a particle's momentum and then position, you will get a different result than if you measured its position then momentum. This is called Heisenberg's uncertainty principle. So the more precisely you measure one quantity, the less precise you will be able to measure the other. And that is shown in this equation here, delta x, delta p is greater than or equal to h bar over 2, where h bar is Planck's constant over 2 pi. So basically, if one goes up, the other goes down. So you can only have one super precise measurement, and the other one you won't know precisely at all. And so our next topic is on the Schrodinger equation, which is the just fundamental equation of motion in quantum mechanics. But before we get to that, we need to define what the wave function is. So invented by Erwin Schrodinger, the wave function psi of x of a system describes how the particle propagates through space as a wave. And so they have this wave function, but now the question is, how exactly do you interpret it? So Schrodinger interpreted the amplitude of the wave function as the charge density of the particle or the system, which turned out to be incorrect. Max Born made the correct interpretation, which is that the amplitude of the wave function describes the probability of finding the particle at that point in space. So if you look at that example wave function picture on the right, you can see that it has different crests and peaks. And so at the point where it's like the most extreme peak or crest is going to be the point at which the particle is most likely to exist at that x value. And so how you find this is you take that value and you square it, and that gives you the probability amplitude, which is the probability of the particle existing at that point, basically. Another thing that we need before the Schrodinger equation is the Hamiltonian operator. So classically, the equation for mechanical energy is this: E equals 1/2 mv squared plus v of x, where v of x is potential energy. And if we write this in terms of momentum, we have p squared over 2m plus v of x. But in quantum mechanics, observables such as momentum, position, spin, etc., are called operators. And so for momentum, when it becomes an operator, we say that p hat, all operators in quantum mechanics are denoted by that little caret on top called a hat. P hat equals negative I h bar del x. And so if we plug this operator value of momentum into the above equation, we get the Hamiltonian operator, where h hat equals negative h bar squared over 2m del squared del x squared plus v of x. And so this is the Hamiltonian operator, or the energy operator. So now we can get to the Schrodinger equation. So when the Hamiltonian operator is multiplied by or acts on the wave function, you get this equation. H hat of psi of x equals negative h bar squared over 2m del squared del x squared psi of x plus v of x times psi of x. or more simply, h hat psi of x equals e psi of x. And so when you solve this equation where you start with the Hamiltonian and you plug it into the equation and then you solve it for the wave function. And as we said earlier, you can then square the wave function to find the probability amplitude. So I believe that's all for this presentation today. We hope, and that's about it for this unit on particle physics. So thank you for coming, everyone, and good luck on any AP test that you have this week.
We encourage you to pursue research on different topics that interest you, and we wish you all good luck on the AP exams this week.